In this video, we are going to discuss about the center of mass of a two-particle system. So first, we will learn about what is the definition of the center of mass. So first, we write the definition, then we will explain the thing. The definition is the center of mass of a system or a body is a point where whole of the mass of the system where suppose to be concentrated. And this point like mass has the same type of translational motion as the system as a whole if some net external force acts on this point like mass as acting on the system. Such a big definition. So I want to tell you what is the meaning of this thing. Suppose this is an object here. Now I am applying the force. I want to translate this object from here to here. Then I am applying 4 force. Here 1, 2, 3, 4. So I'll just translate in this way. In this way, the translation will be done. Okay, you can see. I think you can see. So I'm applying a 4 forces, and with the 4 forces, the object will translate. Okay. Now that is called that. If I apply a force in a particular one force, one net force, if I apply one net external force will be act in a one point like mass, that it will translate in the same way. So like this, if I apply a force here in this particular point, in this point, or you can say here, in this point, I think this is the center of mass. In this point, say object is translating in the same way. Okay, object is translating in the same way. So if I apply force here, the object will translate in the same way, so like this way. Okay, so somewhere here the center of mass is located in this particular pen. So that is the thing called that the center of mass of a system or a body is a point where the whole of the mass of the system are supposed to be concentrated, and this point like mass has the same type of translational motion as the system as a whole if some net external force acts on this point like mass as acting on the system. That means instead of applying the 4 forces, I can apply a single force here so that it will translate. And where I have to apply the force? I have to apply the force in the center of mass. So if I apply the force here, the object will rotate. If I apply the force, the object will rotate. But I want to translate, I have to apply the force here, then object will translate. Okay, in the same way. So that is the thing called the center of mass. Now we will derive an expression for the position of the center of mass of a two-particle system. So for that we will draw. The drawing is there. So this is your axis, x-axis, y and z axis. Now two particle system means here is a one particle, another particle. This is a particle of mass m1, this is a particle of mass m2. You can see position is A and position is B, and these are the position vector. This is the position vector r1 and r2. You know about what is the meaning of position vector. We studied in vector chapter. Now in this system means what? There are two point like mass, and we are going to apply the force externally. So we are going to apply a force here. We will apply one force here, another force here, in this way. But the object is a rigid body, so it will remain, the shape and size of the object will remain fixed. And this object, object A will be applied force in this direction, and another force will be working in this way, in the same line. So this force will give the name, this one will give F1, this one will give the F2, and this one is F12, and this one is F21. Okay, so this F1 and F2 are called the external forces, and F12 and F21 are called the internal forces. So I'll give some name for F12 is the internal force exerted on particle A by B. This force is applied by particle A and exerted on particle A by B. Okay, so this is a reaction force, and this 1,2 is applied by particle A on particle B. Okay, so from the Newton third law, you can say that F12 is equal to minus F21, or you can write F12 plus F21 is equal to 0. That you can write. Now we are going to find out the total force in this entire system. So before that, I'll do something, that this is the object, we are applying force, and this is having some position. Now with that position, we will find out the velocity component. So let r1 and r2 be the position vector of that particular point. So you can write v1 from here. So you find out here, v1 is equal to dr1 by dt, and v2 is equal to dr2 by dt. It will be used afterwards. So first we will find out the total net force. So net force F. So F1 plus F21, F1 plus F12 plus F12 plus F2 plus F21. Now rearrange that one, or you can write F12 is equal to minus F21, so it will cancel. So total force will be F1 plus F2. So this is the net force. Now, according to Newton's second law of motion, A and B, there are two particles, some forces are applied on this one. So net force on F1 and 2, what you can write about this. Okay, so for that we'll give the name of the equation as equation number 1, this one, and you can give equation number 1 this, and this one as a 2. Okay. So according to Newton's third law of motion, you can write F1 plus F12 is equal to d by dt m1 v1. What is the meaning of this one? Rate of change of momentum. Time rate of change of momentum is force. This is equation number 3. Next, F2 plus F21 is equal to d by dt m2 v2. That is equation number 4. Now we'll add these two things. What we'll get? So d will adding 3 plus 4. We'll get d by dt m1 v1 plus d by dt m2 v2 is equal to f1 plus f2 and F2 plus F1. So write down. So already you know this one. This is equal to F1 plus F2. Or you can say this is equal to F. So this is equal to F, net force. Now F is equal to what we got, d by dt. In the third bracket you can write m1, and now we'll use this one. v1 is equal to dr1 by dt plus m2 dr2 by dt. So d by dt, then you can write in this way, d by dt m1 r1 plus vector symbol is must plus d by dt m2 r2. Okay. Now this d by dt will go inside of this one, so it will get d2, double differentiation, d2 by dt square. Then you can write d2 by dt square, or you can write m1 r1 plus m2 r2. Okay. So now we'll multiply the numerator and denominator with m1 plus m2. So you can write f is equal to m1 plus m2, then d2 by dt square, m1 r1 m2 r2 by m1 plus m2. So this is equation number 5. Now see, there are two particle system. Total mass of the system is m1 plus m2. So if I say that the position vector of the center of mass, suppose the center of mass is located in the point C, and the position vector of this particular point is RCM. Then what you can write about this RCM? Total RCM is equal to, you can write total force is equal to F m1 plus m2 into A. Okay. So what are you going to say that if a point of mass m1 plus m2 having the position vector RCM acted upon by the force F, then the equation of motion can be written as, writing with a different color, so that you can write here, write separately, write here. So you can write F for this center of mass, F is equal to m1 plus m2 into A vector. So this we found separately, and we are considering this is center of mass is located in this particular point for these two particle system. Okay, and these two particle system, the total force will be F is equal to m1 plus m2 into A. Now instead of A we can write m1 plus m2. So this position vector, if I double differentiate, will get the accelerations. That means d2 single differential will get the velocity, double differential will get the acceleration. So d2 RCM vector by dt square. That is equation number 6. Now from equation number 5 and 6. So from 5 and 6. So you can write, you can compare. So the m1 plus m2 will get cancelled. So you can write RCM center of mass is equal to m1 r1 plus m2 r2 by m1 plus m2. So this is the formula of the center of mass. So you can write in the form of like coordinates also you can write. So suppose r1 vector will be xi x1i plus y1j, and r2 vector will be x2i plus y2j. If this type of things happen, then you can write xcm. Xcm means the x coordinate of the center of mass will be how much? m1 x1 plus m2 x2 by m1 plus m2, and y coordinate of the center of mass will be m1 y1 plus m2 y2 by m1 plus m2. So you can refer any kinds of book for the formulas and all. Okay. So thank you very much.